So we started off with what we referred to as the parent function, and that's how it should be labeled on your graph. So this is the parent function for absolute value functions. It had a point at the origin, and then its slope, if you think of it in pieces, went up one and over one in this direction, and went up one and left one in this direction. So it makes that V shape. You should have your axes labeled, arrows, and your graph. When we multiplied it by a negative, we said, and you should make a note of it, that it was a reflection over the x-axis. So when there's a negative in front of the function, it reflects it over the x-axis. So it looked something like this. So we know now that whenever there's that negative sign in front of the function, it's going to be flipped. Now when we graphed this function, x plus 5, well, on the f of x axis, it started at 5, and it was an absolute value function that looked something like this. So we said it was a translation up 5 units. Whereas when it was minus 5 outside of the absolute value symbol, it started here. Still the same size and the same shape, except it was translated down 5 units. Translations, reflections, all keep the size and the shape. They preserve them. They keep them exactly the same. So we see that it moves up when it's plus outside, and it moves down when it's minus outside. Now when we added the 5 inside, we saw that it moved the function from the parent function left 5 units. So it looked something like this. So this was a translation left 5 units. Whereas when it was minus, it moved it right 5 units. So it started here, same size and shape, but it translated it left 5 units. So when it's adding inside of the absolute value brackets, addition means left, and when it's subtracting inside, it means move it right. Now here, when we multiplied the absolute value function by 3, we saw that from the parent function to this absolute value function, it was a vertical dilation. So both of these are going to be vertical dilations. However, the bigger the absolute value of the number is, so whatever this number is, the greater its distance from 0, the narrower the graph is going to be. So this is still starting at the origin, but it's much narrower than this graph, which is wider than the original parent function. So the original parent function, PF, was the absolute value of x. So the coefficient in front of this was a 1. So 3 is obviously bigger than 1, so that's why it was stretched vertically, which made it skinnier. It made it narrower than the original. Whereas this was 1/3, which is obviously smaller than positive 1, which means that it's wider than the original parent function. So the bigger this number is, even if it's a -3, -3 just means it's going to be flipped in the other direction, but it's still going to be narrower than the original parent function. So this is a vertical dilation, and in this case, because it's a +3, we're stretching it vertically. Whereas with 1/3, we're compressing it. We're squishing it down so that it makes it wider. Now in this case, these are both going to be horizontal dilations. When you're multiplying inside of the absolute value brackets, it's a horizontal dilation. But one is going to be a compression and one is going to be a stretch. So the same rule holds, and you'll see that it's the same in this case for absolute value functions. The absolute value of 3x is going to be that skinnier one, and the absolute value of 1/3 x is going to be that wider one. That's because this is, again, it's a horizontal compression. And this one is a horizontal stretch. This can affect different things in the future. For absolute value, they look like they're exactly the same. The only difference is you're stretching it in a different direction. So this one is going to be narrower than the original parent function, and this one is still going to be wider than the original parent function. But in this case, we're compressing the original parent function to make it skinnier, and in this case, we're stretching the original parent function to make it wider, and we're stretching it horizontally, whereas when the number was in front, we stretched it or compressed it vertically. So that's the only thing that switches here, is this is a compression, whereas in the other, when the number was in front, it was a vertical stretch, and this is a stretch, where in the other one, when it was a number in front, it was a compression. Finally, just to sum up a little bit, we have different variables in different places here. So we're assuming that we're starting with the original function where it's just the absolute value of x, and we're doing different things to it. When we multiply in front by a positive or a negative value, it's a vertical dilation. We know that it's a stretch or a compression. The bigger the number is, the bigger the absolute value of the number is, the more you're going to stretch it. So the bigger number is stretched more, whereas the smaller number, the smaller absolute value, and the bigger absolute value. The smaller it is, the more you compress it. If it's negative, that's just talking about flipping it, so you're reflecting it over the x-axis. Same thing goes here. Again, with absolute value, it doesn't make much difference. But in this case, when you're stretching it, it's because it's a smaller absolute value, and you're compressing it when it's a bigger absolute value. But again, with absolute value, they look the same. So whether the number is in front or inside, multiplying by the x, it still tends to look very similar. The only thing it could affect is if it has this as well. So this means you're translating it. When it's positive, it's the opposite. You're translating it to the left, you're sliding it to the left. When it's negative, you're sliding it to the right. And then this k outside, when it's positive, it tells you to move the function up. When it's negative, it tells you to move the function down.